Well, today we are talking about adversarial perturbations. So this is basically how do we fool neural networks? So yeah, as far as matters of business, the only assignments remaining for the semester are your final projects, which are your final exam. So there's no in-person final exam. You turn in your project and you are done. Your reading quizzes as usual, and then yeah, if you could fill out the course evaluation and give some feedback, that would be great. Any questions on final projects? Yeah. Yes, so the due date's on Learning Suite. I believe it's the last day of finals. This is the 8th. Is that before finals? Gotcha. I'm pretty sure we want that to be the last day of finals, but I'm going to go to, if it's that way currently, that's how it was for the previous professor. So I'll talk to him to make sure that there's no university issues with moving it to the last day of finals, but otherwise we'll move it to the last day of finals. Good question. Okay. Yeah, Daniel. Gotcha. Okay. All right. So yeah, today we're going to talk about adversarial perturbations. Basically how we can change our inputs to our neural networks to completely fool them without actually changing what the input looks like. A couple of different variants of how to do this, and then how we defend our neural networks from adversarial attacks. So adversarial perturbations exist for humans. You can think of all kinds of, many of these you might have seen before, all sorts of optical illusions. Yeah, which line is longer here? Which circle is bigger on the right? Yeah, what color is this middle bar in that image, etc. Oh yeah, the difference in colors between these two dots on that grid. Are these lines parallel? Are there black dots on this grid? Are these circles stationary or are they rotating? Can you see what this one is? What happens when you stare at the cross? Yeah. So if you stare at the cross, you get a green dot. If you look somewhere else, you don't. Yeah. Okay. So with that in mind, similar tricks can be, well, I won't say necessarily similar, but there also exist tricks that fool neural networks. And so they kind of fall under three categories. Black box attacks, where the attacker does not have access to classification model parameters. White box, and we will also say, and does not have access to the inputs or outputs of that model either. So they have no way of interfacing with the model. White box attacks, where the attacker has complete access to the model architecture and weights. And then gray box attacks, where you have access to everything, you're able to interact with the model, you just don't have the actual model parameters. So this is kind of one early approach where people took a neural network and used an evolutionary algorithm to come up with images that the network responded very confidently to. And so on So for example, we have this kind of wavy lines pattern that was able to convince the network that it was a guitar. And we have this kind of bullseye with vertical lines pattern that convinced the neural network that it was a penguin. So in this case, the adversarial perturbation was designed by an evolutionary algorithm. And so here are some example designs. Can you see any patterns here that make you think of how the network might be fooled by these patterns? The bagel does kind of look like a bagel. Yeah, I'll give you that. Yeah. What else? Yeah, computer keyboard with regularly spaced rectangles, totally. Yeah. So yeah, this is they basically used a collection of hacks to maximize a given neuron. However, and basically this led to extreme pixel values, structured high frequency patterns, and copies of common motifs without global structure. But these are pretty easy to identify as by a human as not being the true class. More recent adversarial perturbations take an image and add some amount of very specifically designed noise to come up with a new image that to the human eye looks perceptually identical to the original image. But yet at the same time, it's this very slight perceptual change is able to completely fool a neural network where the original image was classified as panda with 57.7% confidence, and the perturbed image is classified as a gibbon with 99% confidence. Yeah, and so we're going to look at basically how this works in today's lecture. So the algorithm that's used to do this is called the FGSM, fast gradient sign method. And actually, before I tell you exactly how it works, I'm curious your thoughts. How would you design an adversarial perturbation to fool a neural network? Yeah, what do you think, Tim? Totally. Yeah. So what you just described is very similar to what this algorithm does. So Tim described an algorithm similar to style transfer, where we basically try to push the gradient of, or we try to take the gradient of the loss with respect to the input image and tweak our input image to change the loss in some way. Probably we'd want some sort of loss that incentivizes us to that makes the image classified as some other class, right? So we could have the loss function is the probable likelihood of the word given, and we use gradient descent on the input image to come up to basically make the network think that we are classifying that, to make the network think that image is a given. Yeah, Jared. Great question. Yeah, so Jared's thought is insightful. He says, it seems like you, yeah, you'd end up changing the entire image to be an image of a given. And what do you need to constrain it in some way? And I would say probably yes. You probably want something similar to the content loss in the style transfer lab that makes sure that you preserve the original content of the image while making it be classified as a given. So yeah, these are interesting thoughts. Turns out that the approach that people most often take is very similar, but not exactly the same. So we're going to take the gradient of the loss with respect to the input image, just like Tim suggested. However, we're going to take this only the sign of that gradient. So instead of having continuous values from negative infinity to positive infinity for that gradient, we're just going to take the signs of the sign of the gradient, which will tell us which direction to push each pixel of the image. And the advantage of that is we can create an adversarial image much faster. So that's why this is called the fast gradient sign method. So instead of doing gradient descent over our image, which we know is a pretty slow process, we're just going to get a general direction of what will push this image in the direction of a gibbon, and then add some epsilon times the signs of the gradients with respect to each of the input pixels. Any questions on that? Yeah. What is the sign operator? Yeah, so the sign operator is if the number is positive, then it's 1. And if the number is negative, then the sign is -1. Good question. Okay. So that's the FGSM method. There are ways to defend against this adversarial perturbation approach, but this is a kind of surprising result that these adversarial perturbations are more robust than you might expect. So what we have in this figure is on the y-axis is the source of the perturbation, and on the x-axis is the what we're trying to fool. So we designed a perturbation that would fool the DNN model on the top row, and then we tested it on 5 different models, which go across the top row. What trends do you notice in this grid? And specifically, what models seem to be the best at designing, or I guess, which models seem to be the most easily fooled, and which models seem to be the best at designing adversarial perturbations? And these are error rates, by the way. So higher numbers means that the technique is more confused. And by the way, yeah, this stands for deep neural network. LR, linear regression or logistic regression, one of the two. Probably logistic regression because we're dealing with classifiers. So deep neural network, logistic regression, support vector machine, decision tree, and k nearest neighbors. Yeah, so which of these seem to be the most easily fooled? Yeah, decision trees, even using our adversarial examples designed for other models, are in almost all cases able to fool the decision tree. For those of you who've taken machine learning, do you have any ideas of why that might be? Why it's so easily fooled? Yeah, what do you think, Jaden?
A decision tree is a little bit more simple with clear rules on it.
Yeah. Yeah, so decision trees have very hard boundaries between classes. And so it's pretty easy to, once you push one of those decisions in one direction, then it's pretty easy to know how to confuse a decision tree. Are any of you surprised that an adversarial perturbation designed for a neural network was able to fool a support vector machine or a decision tree? To me, it's pretty surprising because if you remember the way that we designed these, we designed them by backpropagating through the neural network weights. The the designed image was based on knowledge of the neural network weights. And so to see these perturbations transfer means that there are probably some similar things being learned by these different models that make them easily tricked in similar ways. So it's just kind of an interesting thing to think about as we continue. So these are an example of something similar that you can do for text. This technique basically tries to find a single word change that it can make to a sentence that will change the classification of a sentence. For context, this data set is the COLA data set for testing whether something is grammatically correct. And so 1 is grammatically correct and 0 is grammatically incorrect. Anything you notice on these adversarial perturbations? So keep in mind that these are the smallest changes that they could make to the sentence to change its classification. Yeah, what do you see, Jared? Yeah, so the 1 means that a language model predicted that this sentence is grammatically correct, and a 0 indicates that it predicted that it was grammatically incorrect. So what do you see about this first sentence? So which word was changed? We changed the to a, and it went from grammatically correct to grammatically incorrect. What was that? Yeah, you're right. And so to be honest, I don't think this is the greatest example of an adversarial perturbation, because like the most effective, like I would say, we aren't really fooling the network. The network is still doing what it's supposed to do, right? It's still classifying whether something's grammatically correct. They just figured out how to change the input in a way that changes the classification. I walk and Dana runs. I walk, comma, Dana runs. That should be either an and or a semicolon there. So again, it seems like we're not really fooling the network, but we are finding ways to change the input in a way that changes the classification. Yeah, Dane.
Somewhat pedantically, commas technically are the word and in English, so those are equivalent terms.
Interesting. Okay, so I guess we did we did fool the network. Yeah, one more comment. Yeah, so what's the question exactly? Yeah, so the question of why this, well, so I wouldn't say this necessarily works better, but because like the whole point of an adversarial perturbation is to change the classification without changing the input in a way that should change the classification. But the theory is that language rules are easier to learn than images. Maybe that task is easier. So this is another kind of interesting example of the robustness of these perturbations. So this is an original image of a stacked washer and dryer, and they then perturbed the image in 2 different ways and printed out a picture of each of those perturbations, with the idea being, you know, in real life, we aren't feeding images directly into a model. Usually these are images encountered in the wild. And so do adversarial perturbations still work in the wild? And the answer is yes. So this is a photograph of an image without and with adversarial perturbations. And again, even a photograph of the image, the neural network classifies incorrectly according to the desired adversarial perturbation. Is that surprising to you? Yeah, what do you think? Yeah, they took a picture of the altered image. Yeah, they printed out a picture and then took a picture of that printed picture, and it was still classified incorrectly. Yeah, honestly, this surprises me because I would think, there's some probably variance in the printing process and pixel values, and that the adversarial perturbation would probably get washed out, but it turns out that it doesn't. Okay, so this is another approach with the thought that based on the observation that, again, like in the wild, when we actually want to be using neural networks, say on a surveillance camera for classifying whether there's a robber outside your house or something, it's going to have to deal with not clean data. For example, like you're going to have to deal with occlusion and distortion and different poses and different orientations and camera angles. And so, like, is it really possible to design perturbation that can handle that can fool a network in all of those scenarios of distortions and things like that? And so to see if this was still possible, they designed their perturbations to fool the network under some transformation. So this is exactly the same as the original perturbation objective, except instead of x, we have t of x. So we're going to apply some transformation to our generated image. And so this transformation can be pretty general. So in the case that they use, they take crops. So in one case, they take crops of an image. That's their transformation. And so they want to modify the original image such that different crops or rotations of that image are still adversarial. And they showed that they were able to do that pretty well. Then in another experiment, they predicted parameters of a 3D model. That was their x prime. And then the transformation was a rendering of that model. And you can see that, again, those transformations were able to fool the network. And you might be able to see where we're going with this. So in this case, x, the predicted perturbation, was a texture that they then projected on a 3D model and printed out as a turtle. And you can see that, so this is a real life image of a 3D printed turtle that in almost all cases is classified as a rifle. What do you notice about this grid in particular? Any thoughts? Yes, Spencer?
It's interesting because you can see that the one turtle that was not classified as a rifle, that was classified as other, like the lighting's a little bit off compared to the other ones. So I don't know, might be something with like the coloration, but I thought that's interesting.
Yeah, definitely interesting. Any other thoughts? Okay, so yeah, so we're seeing that these adversarial perturbations, they transfer to the real world, which if you're a deep learning practitioner and you want to design safe neural networks, should probably make you a little bit nervous. Yeah, Jacob, what do you think?
I was just thinking, I think we talked about this before, but if you like take away the photo of the total and just look at the background, I can kind of see how that could maybe be a rifle, like just the stock of something, I guess. So
yeah, that's an interesting point. That neural networks often rely on background information to classify. Yeah, any So up to this point, seeing kind of how robust these adversarial perturbations are, what are you concerned? What potential opportunities for misuse can you anticipate these being used for? Yeah, Jaden, what do you think?
I think it's fascinating how I can't figure out what it is that the computer is seeing that's wrong with it. And I wonder, like, the application of this to like human visual processing systems, like you kind of talked about in the first part. You know, I'm like reminded of those YouTube videos of cats that'll flip out when you put a cucumber behind them. And I wonder if it's the same kind of background that's going on there, and whether or not they're going to be able to find out how to like make some kind of adversarial thing that'll kind of alarm a person at first look, and then you don't really necessarily know why.
Yeah, that to me. So that I think is the issue that I'm most worried about when it comes to these adversarial perturbations. And I would say that's actually not what I've heard being discussed as the main concern of adversarial perturbations. But yeah, like we just saw that these adversarial perturbations transfer between models that are trained on different data sets with different architectures. They transfer to the real physical world. So like, have any of you seen those ads or or heard about where they would have film reels, and then every like a single frame out of 30 would be like an image or the Coca-Cola symbol or the image of a Coke to try to kind of subliminal messaging to try to make you want a cold refreshment. Yeah, you imagine similar things like what could be designed to yeah, if perturbations transfer between architectures, can they also transfer to humans, and can humans be influenced, and like are these effects going to be will those the abilities of marketers and things like that become even greater with access to neural networks with gradient signal for designing these perturbations? And after we hear from Dana and Jared, I'd love to hear from some people who we haven't heard from yet today.
I think on the positive side, this actually presents an interesting opportunity for steganography. You could encode a message through deceivingly unrelated objects or images to get a message to someone else.
Yeah, that's an interesting, perhaps positive application. Yeah, Jared.
Yeah, I was just thinking for like in the future, I know people have been looking at using deep neural networks and such for military, being able to distinguish between or classify between an enemy and a friend. And if you can trick the neural network to swap the two, where suddenly a foe becomes a friend and a friend is a foe, then that could be a big problem.
Absolutely. Yeah, any other ways that you can see that this technology could be used for ill?
I know with self-driving cars, sometimes they use deep learning to classify things. And so it'd be scary if someone could just spray paint a little sign on a stop sign or something, so that it just erases that from the vision.
Absolutely. And in fact, people have done that. And yeah, we're going to see some examples of that. So yeah, definitely some concerning potential opportunities for misuse here. Okay, so we're going to talk now about another algorithm for designing perturbations, and this is called a universal perturbation. And basically, the objective function is exactly the same, except we are taking the expectation across all data instances. So the idea is that we want to design a perturbation that will cause not just one image to be classified incorrectly, but any image to be classified incorrectly. And the way we do that is we basically apply this same perturbation update for each item in the data set. So we apply the minimum perturbation that causes this image to be misclassified. And the result is this image here in the center. So if we add this image to all of these images on the left, a whiptail lizard becomes a border terrier, a balloon becomes a Labrador, a lycanid becomes a Brabancon griffin. I wasn't able to fool the network on the Tibetan Mastiff, but flagpole also becomes a Labrador, et cetera, et cetera. And so so people have designed. Yeah, this just shows that these perturbations transfer pretty well. And actually, yeah, we're going to hold off on the example of a universal perturbation. This is another approach where no longer takes into account all the pixels of an image. It takes a single pixel, and they were able to show that by changing a single pixel of the input image, the network was fooled into misclassifying. Yeah.
So I'm assuming most of these examples, they've like trained their network on data that didn't have these perturbations. If you were to then like you do these perturbations, right? Now you're generating a new data set that's perturbed and then go back through and train it. I'm just wondering if someone's done that and if it does classify correctly.
That is a great question. That is a great idea. People have done that, and we're going to get to that in the later part of this lecture. But yeah, that is a great idea for to try to potentially make a network robust to these perturbations. Okay, yeah, so this is another example of a universal perturbation. And so this sticker causes, if you print it out and place it on a table with anything else, most classifiers that are trained on images will classify that entire image as a toaster. So here we have an image of a banana on a table classified with high confidence as a banana, maybe a little bit as a slug. We put the adversarial sticker on the table, and suddenly it's a toaster. And it works, and this universal perturbation also works with stop signs. So you can definitely see the potential issues with this. Okay, some more universal perturbations. This is a perturbation that makes people disappear. So if you live in a surveillance state and don't want to be identified, this could be a good option for you. Or if you're a criminal on the run trying to evade surveillance, yeah, so depends on what your intentions are. Again, this is an adversarial t-shirt. Again, becomes invisible to the image recognition network. Okay, so any comments or questions on these different approaches for adversarial perturbations before we talk about how to defend against them? All right. So there are 4 approaches we're going to talk about today. One is called gradient masking, which basically tries to prevent the network from seeing, or prevent the adversary from seeing the gradients of your classifier. Some passable approaches called adversarial training, which is what you proposed, training on adversarial examples, and then also one on defensive distillation. And then the most successful, to my knowledge, which is which we call the defense GAN. So that this is that idea. Oh, before we do this, actually, I meant to ask you, if you were to defend a neural network, kind of like you proposed one idea, but how would you propose doing it? How would you try to make a network robust to these adversarial perturbations? Yeah, Chase.
So I promise I did come up with this idea before you showed the defense scan thing. But what I do is basically the thing we did with the GANs was have a neural network classifier that's trying to classify the objects, and then an adversarial network that tries to fool the neural network and pit them against each other and train them against each other and get the things to try and be robust to those adversarial networks.
Interesting. So the idea is that basically train again as usual, and hope that. So are you saying use the exact same objective that you would normally train again for?
Same concept. You use different architecture classifier, and then the other one would be something that's trying adversarial fool the.
So interesting. So rather than, so it would be a conditional GAN that takes an image as input and predicts an adversarial perturbation. Interesting. That's a really interesting idea. So that's not how defense GAN works, but I think that could be a really interesting idea to explore. I'm not sure if it's been done, but cool. Yeah. Any other thoughts? How would you defend your classifier against adversarial attacks? I want to hear at least one idea before we move on. What do you think, Daniel?
What if you, because most of the time, I guess when you put neural networks into production, you stop them from learning. But maybe if you had some way to detect when it was behaving irregularly, you have those cases thrown and trained on the network. So maybe if it did start failing, it would at least learn to stop failing soon enough.
Cool. So some sort of online updatable learning thing. I like that idea. Okay, cool. So yeah, we mentioned those 4 different techniques. So gradient masking. Basically, the idea is you want to take a model, and rather than supplying the adversary with a nice gradient that tells it exactly how to fool your network, you have a discrete model with no gradient signal between your instances x and x star. Does that make sense? So for example, you could use a k nearest neighbors algorithm that k nearest neighbors does not use gradients, and use that as a model, and that would prevent an adversary from using gradients to design adversarial examples. Can you think of any possible problems with this? I'll give you a hint. It has to do, the weakness of this method has to do with the grid that we saw with different neural networks on the x-axis and y-axis. We saw, right, that we were able to take a adversarial perturbations designed to fool a deep neural network, and they fooled a decision tree just as well. And so the problem with this is that you can use a substitute model as a black box model, or you can use a substitute model for your classifier, which does apply gradients and design an adversarial perturbation that way. And it does just as well at fooling your gradient-free model. So this second approach is called adversarial training. So like you mentioned, basically during training, we create adversarial examples and supply them as part of the training process. And it turns out that the effectiveness of this approach depends on how high of a weight you put on adversarial examples. It turns out that if your weight of adversarial examples is too low, then again, it's effectively the same as the gradient masking problem, where you can use a substitute model and design adversarial perturbations that can fool the network. And so usually, the training of this definitely works. So this is, on the left is training training and valid and training curves on unperturbed data. And on the right is training curves for perturbed data. And basically, we're able to perform better on perturbed images with adversarial training, but not as well as we did when we just had a normally trained model. So it would appear that the robustness to adversarial examples comes at the cost of model accuracy. Any questions on adversarial training? Okay. And this is another similar algorithm. Okay. We're going to skip this one. Well, I'll just give you 30 seconds on this. So this is an important concept to be aware of. This is called network distillation. So basically, the idea is that you have a teacher model that is large and a student model that is solved. Sorry, training a teacher model that's large and a student model that's small, and you want to train the student model to replicate the teacher model. So usually this is used for trying to make neural networks smaller so that they can run on your cell phone, for example. And we will link it to adversarial examples in a second. And the way that you do this is you train the network to the small network to match not just the classification of the large network, but the logics of the large network. So basically, you are training your student model to match the class probabilities of the teacher model. And it turns out that that is a stronger training signal than training on the labels themselves. So there's a lot to think about and the implications of that, which we aren't going to discuss. But yeah, if you're interested in that idea, feel free to look more into model distillation. Yeah, so basically with model distillation, you're able to achieve a significant reduction in model parameters with minimal cost to network accuracy. Defensive distillation works by distilling a neural network by training on those logics, and it basically softens the gradient so that the network is more robust to perturbations than the overparameterized large network. Yeah, and again, this works decently well, but it is again basically equivalent to gradient masking when you have yeah, where you can use a black box model as a substitute for the student model and still fool it pretty well. So defense scan, this is kind of our state of the art for defending classifiers. And this is the approach. We have a GAN as usual that takes as input a Z vector and generates an image and a Z vector that generates an image, and we want to find a Z vector that creates an image that most closely matches our input image. So basically, this is this GAN will be a preprocessor to anything that our network perceives. And then rather than passing the original image into our classifier, we pass our generated image into a classifier. Any ideas on why that might work?
Because we're still training it to classify real images, it just has those slight noise changes that we see perturbations.
So the classifier does not receive perturbed images as input. So I don't think that's why this works so well. Yeah, what do you think, Dane?
If I remember correctly from the reading, this is essentially saying, what do we have in the latent space that when generated into an image maps closely to the input image? So we're really trying to find something that's analogous to our image based in a trusted latent space. So if we work from that trusted latent space, then we're sort of passing on that trust and only relating it based off of noise, similarity, dissimilarity.
Exactly. And that is why this works, is because, like Dane said, we're getting an image G of Z from a trusted distribution that we know does not have adversarial perturbations as highly likely. Yeah, one more comment before we close. Yeah.
So basically, we're just creating a clean image to classify instead of a potentially
Exactly. We're coming up with a clean image to classify instead of a noisy image. And we're doing that really without applying any modification to the input image. We're just trying to find like the nearest neighbor to that image in our generator space. But kind of a very interesting idea, and I think a pretty promising one as far as defense goes. All right. Well, thanks for coming, and we'll see you on Wednesday.